What we are going to do today is we're going to talk about data in data mining. So last time I introduced to you the overall picture of the different aspects, different stages of data mining. So today we look at the first element that we need to become familiar with, and that's data in data mining. And what we are going to be doing here is looking at the different characteristics of the data. What are the different types of data variables that you're likely to come across? And then how do we visualize data? And once we are done that, then we will talk about, possibly not today, but in the next lecture, how do we perform what we call as the dimensionality reduction or compression of the data, because in certain situations you do need that. All right, so let's get started. All right, not moving. Okay, so from our perspective, when we are talking of data, the simplest way to understand it, of course, we have a collection of vectors, because in every situation, you're going to be describing a collection of objects or a collection of events or a collection of employees whose characteristics you want to define. So essentially, in most cases, what you will have is for every object, assume the object is an employee, then for every object, you have a number of attributes or number of variables or number of properties. And these properties are going to be measured on some scale using some measurement technique. And once you have all those measurements performed or taken care of, then your entire data set is going to look like a collection of vectors. Typically, a row vector will be used for defining a particular record in your collection. So if your record has 20 vectors, or you are collecting record for, let's say, 20 employees, then for every employee, you will have a row vector. And in that row vector, you will have number of columns where each column is going to be defining a particular property. So in the simplest case, this is how the data is going to look like, as shown over here in this particular table. So you can say the first column is just an ID. Yes, please. Why we call it as a vector? Why is it vector? Well, basically, it's a two-dimensional matrix, you can say, all right? But every row of the matrix represents an individual record. That individual record could correspond to a particular customer, or it could correspond to a particular object. So each row that way can be treated as a vector. And once you arrange all these vectors, stack them together, basically you have a matrix. Okay. So why should we do something else? Give me a suggestion. What will you do? I think from the very first lecture, I talked about what is a scalar. A scalar is an individual element. All right. So if you have an age, that is a scalar. You have weight, that's a scalar. But age and weight together, when you put them, that's not a scalar, that's a vector. So that's why we are calling them as, each row is a vector, and you stack those rows for different objects or different employees, then what you get is a matrix. All right. So here is a very simple example. If you look at the example, what we have is the first column is some kind of ID. It could be an ID number or it could be a name. Depends on the particular situation or scenario. And the first property in this particular example is the marital status of the person. So in this case, we are saying, all right, M stands for married, S stands for single, D stands for divorce, and so on and so forth. All right. Then the next column is the annual income column. All right. So this is another property of a collection of people about whom we are talking here. All right. So we want to talk about how much is the annual income of each person. All right. So that's the income column. Then maybe we want to check whether the person owns a house or not. So that's the next column. All right. And then we want to check whether the person owns a balance on their credit cards or not. All right. So if you look at this kind of data, you can say essentially this kind of data is going to be used for some application where you want to build a model that will decide whether a given applicant is a good candidate for giving certain amount of loan. And if certain amount of loan has to be given, what should be the limit of that loan and things like that. So that's why we are making use of some of those properties. But the idea of this example is that each row represents an individual. In general, we can call them as objects, and different columns represent properties or attributes. And for each object, we have a corresponding row. And if we take all the attributes from that row, basically that collection defines a row vector. All right. And the entire collection of all the objects and their row vectors together defines a matrix or a data matrix. All right. So that's basically what we have here. Now you will find that in data mining, the idea of this row vector or column vector is prevalent at each and every stage. The reason why it is prevalent is because when you want to talk about certain operations in the form of mathematical operations, then using vectors and matrices becomes pretty handy, and it allows you to do all kinds of algorithms, all kinds of analysis and things like that. All right. So that's the main idea. So basically you can say that when we talk about objects or persons from a data mining or machine learning perspective, although I showed you in the form of row vectors, but typically if you just want to talk about a particular object, then all the properties of that object will be put in the form of a vector. And typically that vector is called a feature vector. And the feature vector could be arranged along a row, or it could be arranged along a column. All right. So when you are typically talking of an individual object, generally feature vector is in the form of a column. But when you have a collection of objects and you want to talk about all of them, the preferred way is putting them in the form of row vectors. All right. So in this case, if you look at this example here, you can say, all right, we have a picture of a flower. And for this flower, let us say we are measuring 4 properties. The 4 properties are what is the width of the sepal, what is the length of the sepal, what is the width of the petal, and what is the length of the petal. So those 4 properties can be designated as small x1, small x2, small x3, small x4. All right. So that's a general notation. All right. And then if we put all these x1 to x4 in the form of a column, then basically we say, all right, here is a column vector that is representing this particular flower. All right. And this column vector can be then represented as a bold X. Okay, that's the standard matrix vector notation. All right. So that's what we are having. All right. Now, if you look at Another picture at the bottom. We are talking here of objects which are houses. So if you want to talk about different houses, you can say, all right, I can talk about a property, what is the size of the house. So square feet. I can talk about the property, what is the number of bedrooms in the house. I can talk about whether it's a single floor house or a double floor house. So what is the number of floors and how old is the house and things like that. All right. So again, those are the properties. So those will be designated as X1, X2, X3, X4, etc. All right. And in this particular example, these have been arranged along the rows. All right. As I said, it's a matter of convenience, whether you put a row vector or a column vector to describe a particular object. Most often it is the column vector, but one can go either. All right. Now let's look at what are the different types of attributes. If you look back the examples we have discussed so far, you will find that some attributes had continuous value. For example, the income, it could range from any small number to any large number. All right. Or we had some attributes, number of floors, for example, 2 or 1 or 3. Whether a person is married, single, or divorced, again, there are different values that are possible. All right. So depending on what kind of attribute we have, we can give them a particular name. So there are attributes that are known as categorical or qualitative attributes. And within categorical or qualitative attributes, we further have a division. And these attributes are known as nominal or ordinal. So what is a nominal attribute? Nominal attributes is an attribute where you have different possible values. Each value is represented by a distinct name, but you do not imply any order that one particular value is better than the other. For example, eye color. You could have eye color as brown or black or blue. We don't say that blue eye color is better than the brown or black. Those are all three distinct possible values. All right. So a situation like that where distinct values are possible for a given attribute, but we do not have any particular ordering saying that this value is better than the other value, and that kind of attribute is known as a nominal attribute. Yes, sir. We'll come to that. Okay. Then within the categorical or qualitative attribute, we have what we call as an ordinal attribute. The difference between nominal and ordinal is, again, you have distinct names for different values in the ordinal attribute, but we assume some kind of ranking. For example, you have an athletic event at Olympics, all right? Somebody wins a gold medal, somebody wins a silver medal, somebody wins a bronze medal, all right? So somebody won a medal. What kind of medal that person won? We can say gold or silver or bronze. Now everybody knows gold is better than silver and silver is better than bronze. That means there is an order that has been implied. We are saying one particular value is better than the other value. Or for example, grades. You can have an A grade or a B grade or C grade. Obviously, everybody prefers to get an A grade because A grade is better than B grade. All right. So attributes like that are examples of what we call as ordinal attributes. All right. Of course, we have majority of the attributes as numeric or quantitative attributes. All right. Again, within the category of numeric or quantitative attributes, we have two possibilities. We can say, all right, we have an attribute which is an interval attribute, or it's an attribute which is a ratio attribute. So what is the difference between the two? In the case of interval attribute, the measurement scale used to measure the attribute value has an arbitrary zero value. That is, the zero value for that attribute is arbitrary. It has no relationship with the reality. A very good example is the measurement of temperature. In the temperature, you could be using Celsius, or you could be measuring temperature in the Fahrenheit. All right. In Celsius, you have a 0-degree temperature. All right. Fahrenheit, the similar temperature is 0 degrees Celsius is considered 32 degrees. All right. These values are taken purely arbitrarily. For example, let's look at the second type of attribute first, then we'll come back to this. Ratio attribute. Ratio attribute again is measured on a numerical scale, continuous scale, but in this case, you have an absolute zero. For example, you are measuring the length. So length has an absolute zero value. All right. Or you are measuring weight. Weight has an absolute zero value. All right. So if I say one particular item has a length of 6 feet and another item has a length of 12 feet, I can say that the second item is twice as longer as the first item. Let's go back to the Celsius temperature scale. All right. If I say today the temperature here is 20 degrees centigrade, and let's say in Windsor it is 40 degrees centigrade, does it mean that Windsor is twice as hot, or Detroit is twice as cold as winter because the ratio is 2? That's not correct. All right. Because 20 degrees centigrade and 40 degrees centigrade, in terms of the temperature, in terms of the feeling, you get different feeling. Not like the length, okay, this is twice as much or 1/2. All right. That's because the 0 point has been selected in an arbitrary fashion. All right. So any attribute where the 0 point is selected in an arbitrary fashion is interval attribute, and any attribute where 0 point is an absolute zero, then that's a ratio attribute. All right. So these are 4 different types of attributes. What are some of the properties that are associated with these attribute values? Now, if you look at the nominal attributes, the only property that you can associate with nominal attributes is the distinctness. That is, if there are 2 different values of a nominal attribute, then those 2 different values represent 2 distinct situations, let's put it. Okay. In the case of attributes where you have an order, then order is also implied on top of distinctness. All right. For other attributes like ratio or interval, you might apply addition operation, you might apply multiplication operation. So depending upon the nature of the underlying attribute, certain arithmetic operations are possible and certain arithmetic operations are not possible. And this is important to remember, because when you do some manipulation while you are building your models, then obviously those manipulations have to ensure that underlying attributes are, that is, those manipulations are valid for the underlying nature of the attributes. All right. And of course, when you have attributes, sometimes you want to make some changes to those attributes. And those changes are what we call as transformations. So there are certain transformations that are possible for different kinds of attributes. So in this table, we are showing you some of the examples of those transformations that are possible. All right. Now, in computer science, most of the time when you have talked about variables, you have talked about whether it's a continuous variable or it is a discrete variable. All right. So from that perspective, you can say that attributes could be discrete attributes. And in the case of a discrete attribute, only finite values are possible. And of course, these discrete values are often represented as integers or binary variables. All right. Or you can have a continuous attribute, which is basically same as using a real number to represent a variable in your program. All right. So these can be measured using number of digits on a scale that could be small or it could be large. All right. And typically, anything you consider as a floating point variable, typically you will say, all right, that's a continuous attribute. All right. So suppose you have started working on a data mining problem, and the first step is always to have a collection of data. So you have collected, let us say, you took thousands of objects for which you want to perform data mining. Let's say that you want to figure out what kind of background, let's say, makes certain students more successful compared to the other students. All right. So for building a model to answer that kind of question, you will basically go to the registrar's office and with due permissions, you will basically collect data for last few years of the students who have enrolled at Oakland and who have graduated. So you will know, what courses they took, how they perform, and of course, going back to their application for admission, etc., you will know what background they had, where did they go and did the high school. You might have their demographic information. You might know in which neighborhood they were living and all kinds of things. So assume that you have collected such data for a given problem. So once you have that data, how do you characterize that data in a broad sense? All right. So basically, there are three components to characterize a data collection for a given problem in a broad sense. Number one is the dimensionality. So dimensionality refers to how many attributes or how many variables are being used for a given single object. So going back to our example of students, you can say, all right, how many attributes we are using in our model for each and every student. So if we are characterizing each and every student using 100 attributes, let us say, then basically we can say that the dimension of our problem is 100. So we have 100 dimensional data set. All right. So that is what we mean by dimension. Now, obviously, as the number of dimension grows, two things happen. Number one, the size of these vectors that represent each and every student, their size becomes large. All right, instead of 5-dimensional, now you have a 100-dimensional vector. And if you have more variables, its size will grow up. All right, which means for your entire collection, the data size grows because now you are recording many more items or many more attributes for every student. That means you're recording more data, so that your data size goes up. At the same time, what happens is, and I'll show you in next slide or so, as you increase the dimensionality, there is a corresponding demand, indirect demand, to increase the number of examples in your data set, or increase the size of your data set in terms of the number of objects or number of students for the running example that we are talking. All right. And that indirect increase is kind of termed as what we call as the curse of dimensionality. And oftentimes people like to perform what we call as dimensionality reduction to reduce the size of the data, etc. All right. So we'll be looking at that. But that's one way to characterize a data set. All right. Another way to characterize the data set is whether data set is sparse or not. Think of a situation where you have a large collection of attributes, and these attributes mostly are binary in nature. That means whether a particular attribute is present or absent. So just, one or zero are the answer. All right. So if you have a large collection of attributes like that, your feature vectors typically will be mostly consisting of ones and zeros, because a one will indicate that particular attribute is present, a zero will indicate the particular attribute is absent. All right. So in certain situations, it turns out that you might have large number of attributes. For example, you might have thousands of attributes, but for every object, only a very tiny fraction of those attributes is present in that given object. That means for every object vector, only very few entries are ones, rest of the entries are all zeros. So if you look at data of that nature, basically you can say that you have a kind of binary matrix where majority of the values are zeros and very few values are ones. So that is what we call as a sparse data set, or that data is sparse. All right. The third one is resolution. Yes, please.
Sparsity means imbalance in short.
Oh, class imbalance. Yeah, we'll come to that. We're not talking of class right now. So
In short, like
as I said, we have not introduced the class right now. So we cannot, there's no point in mentioning imbalance. Okay. The third angle is resolution. Let's look at the example where you are trying to collect data about, you want to create a picture of different households in the state of Michigan. All right. Now you can create this data set at an house level. That is, you can look at each and every house and you can record how many people are living there, what is the income, who owns, what is the property value, and all kinds of attributes. All right. That will be at a very fine level of details that you're collecting data. All right. If you don't want to collect data at such a fine level, what you may say is, well, let me not collect data at each individual house. Let me collect data based on the neighborhood. For example, I can go to a particular neighborhood which has 20 houses. In that neighborhood, I can take the average over those 20 houses and use that as a representation. Now, instead of neighborhood, you might say, well, I'm going to go one step further and I'll collect the data only at the zip code level, or at the city level, or at the county level. So this is what we mean by resolution. That is, you could have data at different levels of granularity or at different levels of resolution. Obviously, if the data is at the lowest level or at the finer detailed level, obviously that data is going to be a little noisy because you are looking at things in a very fine scale. So you will see lots of variations, a lot of noise. But if you go at the little higher level, what happens is you are aggregating the data, and that way Small noises, small variations will get suppressed and data will be less noise. So depending upon at what level you want to perform or operate, you will have these characteristics of the data. All right. So let's look at this idea of curse of dimensionality. So here we have three pictures. Let's look at the first picture on the left-hand side with d equal to 1. All right. So let us say that in this case, the dimension is only 1. That means all the measurements are being made only in one dimension, maybe the length or weight or whatever it is. All right. So let us divide this range of 0 to maximum value that is possible into, let us say, 3 intervals. All right. And we have one measurement within each interval. So basically we have 3 measurements, or you can say we have 3 examples such that we can place an example in each interval. All right. Let us go to dimension equal to 2. And let us extend this idea in 2 dimensions. So now we have 3 by 3 group of cells in 2 dimensions. And now if we want to place one example in each cell, we need how many examples? We need now 9 examples. All right. So earlier we needed 3 examples. In 2 dimensions, we need 9 examples. All right. If we go to 3 dimensions, d equal to 3, and we want to achieve the same level of fillingness, that in each cell we want to fill in only one example, then in this case we are going to need 27 examples. All right. So as you keep increasing d, you can see that the number of examples that we need to get the same level of density in our space or in our cells, the number of examples keep growing. Not only it is growing in an exponential fashion. That means when the dimensionality is very large, you do need a much larger number of examples to fill in your entire data space to reasonable amount of density. And then you can try to build your model. On the other hand, if the dimensionality is small, you can get the same level of density in your data space with much fewer examples. So this indirect demand on the number of examples is what we call as the curse of dimensionality. All right. Now, typically you will be building your models using one of these different types of data sets. So let us say what are the different types of data sets that people typically use for data mining. The most common type is what we call as records, which will be in the form of either data matrix or document data or transaction data. And we'll look at those examples in the following slides. Or your data set might be representing graphs. So in that case, your data set is going to look like a graph structure. Somehow there is encodes that. Or your data set might have some kind of order in it because it's an spatial data or temporal data or sequential data or genetic sequence data. Or it might have ordered but unstructured. For example, it might have a collection of pictures as your data set, or you might have a collection of videos as your data set. So these are different types of data sets that people deal with when they are doing data mining or machine learning. So record data is similar to what I showed you in the very first slide. Basically, you have rows and you have columns. Columns correspond to different properties, and each row represents one particular record item. All right. Data matrix is basically when you put these rows in the form of a stack, you get a data matrix. All right, so here you have a collection of rows, and put together, they form a data matrix. All right, that is typically how most of the data sets that you will be using on the internet, if you want to download, that's the form they will be in. All right, so another one is what we call as a term document matrix. This kind of data is used when you are dealing with text documents. So suppose you have a collection of pages or collection of text documents. What you can say is, if you look at this example, what we are showing is there are 9 documents, D1 to D9. So those are being represented as columns, along the columns. And let us say that we have defined certain attributes. And in this particular case, the attributes are nothing but certain keywords or terms that are supposed to be present in these documents. All right. So those keywords or terms are shown as rows. So there is a first row with the term human, all right. Second row with the term interface, and so on and so forth. So what we are doing is we are looking at these 9 documents, and we are saying in which document the term human appears. If it appears, we mark it as 1. If it doesn't appear, we mark it as 0. All right. So basically, we have a Boolean matrix, a matrix of ones and zeros, where if 1 indicates that there is a presence of a particular word in a corresponding document represented by that column. So words are being represented by rows, columns are being represented by, documents are being represented by columns. All right. So if you look at now this example or this representation and think of a very large collection of documents, and let us say you have 100 terms there and you have 1,000 documents, then obviously for every document, only a very small fraction of these 100 terms will be present. So the resulting matrix will be highly sparse, similar to what we have here, more or less a sparse matrix. All right. So when you are doing these kinds of problems, you are likely to come across sparse matrices. All right. So this is what we call as a term document matrix. In certain problems, you are dealing with what we call as transaction data. So you have a collection of transactions. So each row represents a particular transaction, and the items involved in that transaction, what got bought in that transaction, basically is what is represented. And you can see that one can easily represent this transaction data also in the form of a transaction item matrix. We can, use the same idea of term document matrix and actually represent this also in a similar fashion. All right. So it depends on, what is the starting point. Sometimes if you're dealing with transaction data, this will be your starting point. And if you want, you can convert it into a term document matrix kind of representation. Graph or linked data, basically you will define different nodes and you will define connectivity between those nodes through links. All right. And then the nodes might have certain properties. Those will be defined and that will become your graph or linked data. Sometimes you have what we call as the order data. For example, you might have sequence of transactions A and B, then followed by transaction D, followed by transaction C and A, etc. All right. So that way you have not only the transactions, but you also have them in a particular order or in a particular sequence. If you are doing bioinformatics work, then you might have a genomic sequence data where you represent the the different genomes through a sequence of these symbols, G, G, T, T, C, A, etc., etc. All right. So that will be your data. You might have what we call as the spatiotemporal data. That is, you might define what is the temperature at different locations. So basically, locations are defining the spatial aspect, and temperature is defining the measurement. So you have a spatiotemporal data, and you might define this as an average monthly temperature of land and ocean. Order data, for example, you might have a video sequence representing your data. Now, your video sequence is nothing but a collection of individual video frames. So each frame is an image or a picture, and each frame is spatial data because you have image is going across horizontally and it's going down vertical. And you can see at different horizontal and vertical points, you have different color values. That is how you're defining your image. All right. And if you put these images one after the other in a sequence, that becomes video. All right. So an order data, video is an order data which has an spatio-temporal characteristics. It's spatial in 2 dimensions, but temporal in the 3rd dimension. So it's a 3-dimensional data. Now, how do we get hold of data for doing data mining? Suppose you're interested in building, you want to practice data mining, you want to practice model building. All right. So how do you go about getting some data so that you can build some models to, get some practice to increase your knowledge and things of that nature. All right. So there are different ways of finding data for data mining. The easiest approach is to go for existing data libraries. There are a variety of data libraries that are up on the internet. Many of them are open source, so you can get the data without any payment. Some of them do require membership or some payment. All right. So depending upon your needs, you can actually go and browse through those libraries and see if there is any data set that will be of use to you or of interest to you. The second way is to gather your own data. And third is to extract or perform scraping from internet to get your own data. All right, so these are 3 broad ways of getting data for your projects. All right, so let's look at some more details. Here are some examples of existing data libraries that you can browse through and look at. Data.gov is a fantastic library where you can get data about all kinds of things related to housing, related to general public interest, census data, household incomes, retail information, all kinds of things. All right, so it's a biggest repository of government data. All right, so you can go there, and what you will find is that they do have some interesting APIs that you can use to basically download or specify what data you want and directly download it to your Python or Excel or whatever software you want to use. All right. There is another site called iPumps, which is again a government funded site which collects a lot of data and makes it available for different purposes. So you can browse through that and again see what kind of data you can find from there that might be of use for your project. All right. There is a hospital compare data sets where they compare different different hospitals in terms of all kinds of parameters, all kinds of attributes. There is a National Center for Environmental Information. You can go there and collect data or get data related to environmental aspects. All right. So many of these sites are government sites, so you can actually go there easily without any issue and download the data without any problem. Sometimes if you want to make use of an API, you possibly need to register and get an ID so that you can use that ID in your API calls. All right, so you can do that. There are some libraries that are specific for machine learning and data mining, where people who have collected data for different data mining and machine learning projects, after using that data, they have put it out there. This is all in the open source. You can download that data and perform whatever task you want. All right. So there is a machine learning repository at UCI, University of California, Irvine, one of the oldest libraries. You can go there and browse through. They have a large collection of data for all kinds of problems. I already mentioned Kaggle last time or in the previous lecture. So Kaggle also has lots of data. So you can go there and collect data from there. If you are interested in a lot of data related to politics, etc., then I think there is a site called 538. You can go there and check out. Similarly, there is another site called Pathmine. You can check out there. So these are some of the examples of sites where you can go and browse through and download data for your problem. So these are making use of existing libraries that you can go and check out. For certain applications, for certain projects, especially if you're working in an organization, in a company, your manager might put you on a project and might tell you, okay, we need to do this project. So in that case, you have to get or collect data, and you might be able to collect that data by looking into the different databases that your organization is maintaining and see whether those databases contain the relevant data that you need. Or in certain situations, you may need to do a little bit of work to collect that data. All right. So in certain situations, you will be required to do some additional work to gather data, especially in a business setting. All right. So if you want to see how that can be done or how this has been done, so we did a project many, many years ago, and the link is here. This was the project related to looking at the quality of the glass that is being manufactured by Guardian Industries. So we wanted to check the quality of the glass and relate it to the different parameter settings for the operation. So we needed to collect that data and then build a model. So depending upon your particular project or application, you might need to do that and figure out how to do it. All right, so that's where you have to gather your own data. Of course, in many cases, people like to scrap the data from the web. So it's an automated method which you can use to extract large amount of data from websites. And how many of you are familiar with some web scraping? Anybody has done any web scraping here? No. All right. There are two links here. I strongly recommend that you take a look at these two links. Both of these links give you very simple examples of doing web scraping, and that will get you started, and you will have some ideas how to do it, and it will be very useful and beneficial for you. All right. So I strongly suggest you do that. So let us assume that you have either downloaded the data from one of these existing libraries, or you have collected the data, or you have done some web scraping and you have the data. So what you need before you jump into using that data to do some modeling. Remember, I mentioned that you need to do a lot of pre-processing and data cleaning. So here are some examples of some pre-processing or data cleaning. All right. So let's look at some problems related to data quality. All right. Pretty common situation when you are collecting data is there's a lot of duplication and incorrect names and spellings if you are especially collecting data for direct mailing and things like that, or customer information. That's what will happen. Sometimes the values of some of the fields are missing. People don't like to give certain information, so they might be missing. Or sometimes people put in some incorrect value. For example, somebody might be asking, all right, please enter your age value. And somebody might, just for fun of it, might enter, 6 months or 1 year or 105 years. Okay, so the values are incorrect or they just skip that entry. So either you have outliers or you have noise. So basically, you need to take care of some of these issues before you can proceed any further and do any work. All right. So here is an example of how to clean noisy data. Again, this kind of work will depend on particular type of data that you are working with and what kind of issues it has. So in this case, let us say that we are working with data which is changing over time. So in some sense, you can say it is a time series data. All right, so we have a collection of observations over a period of time. All right, so if I take that collection and make a plot of it, it's going to look like the plot that is shown in the left corner with the blue ink. All right, so you can see that this data is noisy, and it might not be useful if I use it directly. It might need some kind of cleaning. All right, so depending upon what particular cleaning application I use here, I'm showing you the result of cleaned data, that is applying cleaning on this data in the right hand side picture. So you can see the same plot, but now the data has been cleaned and it is being shown. So you can see that clean data is making a lot more sense than the noisy data. So many times you will need to perform some kind of cleaning operation. What is an outlier? So outliers are data objects or readings that are considerably different from most of the other data objects or other data object values. All right. So if you look at the picture on the right hand side, we have a picture of green apples, but in the center you have a different apple. So gala apple or something like that. All right. So in this particular case, you can say that that particular apple is an outlier. All right. If you look at the left hand side, we have a set of readings represented through points in the two-dimensional plane, but there are a number of 3 readings that are enclosed in that red circle kind of thing that are quite different from the rest of the reading. All right. So those 3 readings will be considered as outliers. And the point is that if you don't remove those outliers or do not detect them before you build your model, then what will happen is that those outliers will come into play when you are building your model, and they'll distort your model. The model will not be good if the outliers are included in the model building process. So what you want to do is you want to get rid of outliers so that you can have more confidence in your model. All right. Missing values. Oftentimes, some of the values will be missing. All right. What are some of the reasons? Information is not collected. People sometimes decline to give some information, so it's not there. In many cases, the attributes may not be applicable to all cases. So you might have designed a survey or and some instrument through which you're collecting data. And some of those items may not pertain to some subjects. So in that case, the subjects will leave those entries blank. All right, so you will have missing values. So how do we handle missing values? There are a number of ways in which one can deal with missing values. Suppose you have 10,000 records, that is, you have 10,000 objects or 10,000 data vectors, each vector representing an object or a situation. And out of those 10,000 records, you find that there are 100 records for which some of the values are missing. In such a situation, the easiest solution is to just discard those 100 data vectors, because 100 vectors out of 100,000 vectors is really not a significant number. So throwing them away or not using them is really not going to impact your model. So in many situations, you can just discard the objects or the reading or the vectors which have missing values, provided the number of such vectors is a tiny fraction of your overall data size. All right. Sometimes you have many more missing values and you cannot really throw them away. So what you need to do is to figure out some trick so that you can fill in those missing values. All right. So one way is to estimate those missing values. How do you estimate those missing values? Again, one can use different techniques. It's simple will be, let us say one can replace the missing values with the most frequent value. You could calculate what is the mode of this particular variable and use that. Or you can take the mean and say, all right, I'm just going to fill in with the mean value, or some other trick you can use. So the point is that one can think of different ways of filling in those missing values. All right. Sometimes you look at a surrogate variable, another variable which kind of varies up and down in more or less in sync with the variable for which you have a missing value. That is, identify a variable that has a good correlation with the variable whose value is missing, and use that surrogate variable to make an intelligent guess for what will be the missing value. All right. So these are some of the tricks or techniques that people use to fill in the missing values. All right. And when we use sklearn library for doing the modeling, you will find that sklearn library does give you a couple of options, couple of choices in terms of how you want to fill in the missing values. So when we go over some examples, I'll show you how to fill in some of those missing values. So you have to fill in the missing value, you have to get rid of noise, etc. So continuing with that, let us say we want to continue with data cleaning. So as I said earlier, this is a major effort, especially when data comes from multiple heterogeneous sources. You have to get everything in the same format. You have to figure out what different fields imply in different databases and things like that. It also involves detecting duplicate values, outliers, missing values, correcting entry errors, reconciling field names and representations from different sources. And some of those things we already looked at earlier, all right? So what other pre-processing one can use to make your data better? or improve the quality of the data or get a better modeling done using the given data. So some of the pre-processing operations that people typically use are what we call as aggregation, sampling, feature extraction, discretization and binarization, attribute transformation, dimensionality reduction, visualization, and feature subset selection. So these are different aspects that are involved in data pre-processing, and we are going to go over the one by one. Aggregation idea is simply combine two or more attributes into a single attribute. Why would you want to do that? The basic philosophy is that aggregation can help us in data reduction by reducing the number of attributes or objects, all right? Because you are merging or you are creating a new attribute by, let us say, merging 2 or 3 attributes. That means you are reducing the number of features or number of attributes in your data. So in a way, you are reducing the dimensionality. So that's a good thing to do, all right? Aggregation can also be done to change the granularity of the data. For example, we can aggregate cities into regions and regions into states and so on. So again, when you do the aggregation, the noise level goes down. So basically, aggregation helps in improving the quality of the data from a noise perspective. All right. Sampling. In many instances, your data set might be very large, and you may not have hardware resources to handle such a large data set. For example, you might have 1 million records, and the system that you are working with is not able to handle that many records. So what you will like to do in that situation is to take a subset out of those million records. What should be the constraint on this subset? The subset that you will take should be a representative subset. You cannot just arbitrarily take first 100,000 reading, first 100,000 records and say, okay, that's what I'm going to work with. No, you have to pick a subset which maintains the representative nature of your entire collection. So this process of selecting your subset is what is known as the sampling. So you need to perform in certain situations a sampling of the entire data set to get a smaller data set that your system can handle, that you can work with. All right. And the reason is, of course, if you want to work with the larger data set or full data set, either you buy new hardware or it might take a lot of time. So you want to get quick and dirty results. So that's why you're doing this. All right. So what are the different types of sampling? How do we ensure that you will be collecting a representative set? All right. So one is what we call as a simple random sampling. In this case, every record in your data set has an equal probability of getting selected. So what you will do is you will use some kind of random number generation technique to select samples or items from your record, from your data set at random, not in a particular algorithmic way, but in a random fashion. With the idea that random selection will maintain the representative properties of your entire collection. All right. Sometimes you do sampling without replacement. What this means is that as each item is selected, it is removed from the population. Sometimes you do the sampling with replacement, and sometimes you do it without replacement. All right. So what you're doing with without replacement is that basically you remove the item after it has been selected. So what happens is that if the item has been removed, obviously it cannot be selected again. All right. But if you are not removing the item, then that item can get selected again. So that is the difference between sampling without replacement and sampling with replacement. In one, yes, please.
What's the difference between sampling with replacement
And
and simple random sampling?
simple random sampling. Yeah, actually, simple random sampling has these two ways of doing it. Okay, so you can say these two are two ways of doing simple random sampling. All right. I should have put another tab there and it would have gone to the right answer. All right. So the next one is what we call as a stratified sample. For example, suppose you have your million records, and in the million records, these are of different persons, let us say. And of course, there are males and females in those records. Now, there are certain applications or certain situations where you are doing modeling and you want to do the model in a way that model takes into account whether the underlying subject is male or female. So what you want to do is you want to do a sampling out of male population separately and a random sampling out of female population separately. So anytime you do that, that will be what we call as a stratified sampling. Or you might say, all right, I want to study the health and I want to look at people who are smokers and people who are not smokers. So what you will do is you will do the stratified sampling by grouping all the smokers in one part and then picking at random people from there, and then non-smokers in another part, and picking people from that particular part. So anytime you do that, that is what we call a stratified sample. Here is a simple illustration of sample size. So basically, out of all the data points that you have, if you select 8,000 points for a particular example that is shown here, you get a representation in 2 dimensions as shown in the leftmost picture. If you collect only 2,000 points, that is what you will get. And if you get 500 points, you get the representation on the right hand side. And you can see that more or less we are able to maintain the patterns in these 3 pictures. All right. So that's basically what we mean by sampling. And the main idea is to reduce the computational load, memory load, so that you can get your results with the given resources in a given amount of time. Sometimes you want to create new features that you think will help you in getting a better understanding of the situation, as well as they will help you in reducing the dimensionality of the data. All right. So for feature creation, there are 3 general methodologies. One is what we call as feature extraction. This is a domain-specific methodology. So if you are working, let us say, in the medical domain, maybe a physician or a medical expert can tell you what will be the good variables or good features to look at for a particular disease modeling. So that is what will happen there. So it's a domain specific, so there is really not much we can say in general about this approach. All right. Another approach is to map your data into a new space. Whatever representation you are using, change that representation to a new space where it might help you to create, get better features. All right. Third one is feature construction, where you combine some of the existing features into a new feature. All right. Now, I'm sure all of you have heard of deep learning. The major reason why deep learning has taken off and has become so popular is because the deep learning allows the computers to learn the features also. In machine learning, we don't learn the features. The features are provided by experts, or whosoever is collecting the data, that person will define the features. But in deep learning, we give to the system raw data, and the system itself learns from that raw data what are the useful features to look at so that it can perform the given task. So that is a big reason for the popularity of deep learning, and it's a major strength of deep learning. All right. So let's move on. So here is an example of mapping data to a new space. All right. Let's look at the central frame here, which shows 2 sine waves plus noise. So it's a time series data. All right. Now, this time series data is being represented as a set of readings over a period of time. All right. Now, what one can do is one can map this time series data into a different representation, which is known as the frequency domain representation. And in that representation, our time series noisy data is going to look like as shown in the last panel in this slide under frequency domain. All right. So you can see that it is the same information, but it is being represented in 2 different ways. All right. Now, what is the advantage in this particular case of frequency domain representation? The advantage is that if you look at the frequency domain plot or graph, you will find that most of the small values are below 50 or 55. There are only 2 values or 2 peaks that are very high. All right. So it turns out that these small peaks are essentially representing the noise, and large peaks are the ones that are the real information that you have, or that is what your actual data is without any corruption or without any noise. So if I make a simple rule that remove all the small peaks below 50, 55, and just keep everything above that, what I have done is through this mapping, I have removed the noise, I have created a new representation, which is much cleaner and much better and tells me gives me much more information. All right. So sometimes people use this kind of representation. Now, I don't know whether any of you have looked at frequency domain represent. Anybody here familiar with Fourier transform, or anybody who has? So if huh? Right, there are a number of transforms. All right. So if you have used Fourier or wavelet transform or Hart transform, there are a variety of transforms which take information from one domain, typically the time domain, and map into a different domain, which is kind of a spatial domain or frequency domain. All right. So one can use such representation in certain situations. to clean the data to get a new representation and things like that. All right. Binarization. Sometimes what you like to do is to take your categorical features and put them in the form of a representation, which is known as 1 out of M representation, or representation more commonly known as one hot vector representation. So if you look at, for example, your letter grades A, B, C, D, and E, you may want to represent them using a 5-component binary vector. So A will be represented as 1, 0, 0, 0, 0. B will be represented as 0, 1, 0, 0, 0. That means you have only one value in the 5-component vector. And the position of that value indicates what is the underlying grade. So if it is at the first position, underlying grade is A. If it is second, B, and so on and so forth. Do you have any questions, sir? Yeah.
Is it this the one hot encoding?
Yeah, this is known as one hot encoding. Okay, very same. Or 1 out of M, either way you can call it. All right. The second one is binarization of continuous attribute. For example, you are measuring age. Instead of carrying the actual age, you might carry, young or adult or old by chopping off the age values below 35 for young, between 35 to 55 as adults, and 55 and above as old or something like that. All right. So that will be what we call as binarization of continuous attributes. And also, if you're dealing with pictures, your original picture might be a color picture or a gray level picture. And by certain thresholding operation, you can convert that into a binary picture or a 2-level picture or a 2-tone picture. Okay. So sometimes that kind of pre-processing is used to reduce or to represent the data in a form that is much more suitable and much more workable. All right. Sometimes the continuous attribute has to be discretized into number of intervals. So you could choose equal interval width. For example, you can take age 0 to 25, 26 to 50, 51 to 75, 76 to 100. Or you can choose the bin locations to ensure that every bin has equal frequency. Suppose your data is such that you know that it has a lot more persons in your data set who are 50 and above. So if you follow the equal width approach, then some of the bins will be not full much, some of the bins will be overloaded. So what you may want to do is to make the bin locations adapted such that all the bins have equal filling in, or they are filled in by equal number of examples. All right. So those are possible, and depending upon what you like to do, you can pick any one of these 2 ways. Feature construction. Basically, what you do is you try to put together number of features that you have, raw features, combine them and create a new feature. All right. So there is an example shown here in the slides, which basically has an example from a project that we did many years ago. And basically, each customer has 32 attributes or 32 properties. And these are shown here in the slide on the right-hand side. And by looking at those properties, we figured out that one can create gender and marital status attribute by looking at different title codes. So we had different title codes representing, persons. So if you look at what is the meaning of each and every title code, then based on that, you can guess what is the gender of the person, what is the sex of the person, and what is the marital status of the person, and basically combine them to create a new feature, which will then not use all these codes, but will be using that particular feature. So this is just a simple example of creating a new feature based on number of existing measurements or number of existing features. All right. Another example, again, I'll not mention here, but you can again look at different attributes, and you can combine some of them to say whether the underlying vehicle is a compact vehicle or a sports car or a family sedan, and so on and so forth. Okay. Sometimes you want to transform the attribute. So instead of using the actual measurement, you may want to use the absolute value of the measurement, discard the sign, or you may want to use the log, especially if some values are very high, then you may want to use a log of that, or e to the power, or x to the power k, or any other function. Second bullet is the most important bullet I want you to remember. That is, most of the time, you should be doing what we call as normalization of your attributes. Because when you measure attributes, some attributes have a smaller range, some attributes have a very large range of values. As an example, suppose you are measuring attributes or you are representing different employees in an organization. So age is an attribute, let us say, or a number of years in the service is an attribute. All right. So we know that that particular attribute has number of years in a service. Maybe it will be from somewhere from 0 to 50 years or 70 years. All right. That's the possible range for that. All right. Suppose another attribute is the income. Income could be $10,000 to, let's say, $1 million. So this range is pretty large. All right. So if you combine these two variables, age and income, in certain mathematical expression, since the income variable has such a large value, this variable is going to dominate your expression. Age is not going to affect much. All right. So what you want to do is you want income not to dominate your expression. And to do that, what you want to do is you want to perform some kind of normalization operation on your attributes. So what is done is we basically take each attribute, we calculate what is the mean of that attribute, what is the standard deviation of that attribute, or what is the minimum value of that attribute, what is the maximum value of that attribute, and use that information to normalize the values of attributes such that after normalization, all attributes are lying in the same range of values, typically between 0 and 1. So when all of them lie in the same range of values, then obviously no particular attribute is going to dominate the calculations. That means your model is not going to be affected by any particular attribute as the model is being learned or as it is being built. Every attribute will have equal chance of affecting the model. Okay, so that's very important. Let's talk about similarity and dissimilarity. So we are representing different objects or different employees through a number of attributes, which ultimately leads us to represent each person or each employee or each object as a vector. So given two vectors representing two objects or two employees, how do we say how similar are these two employees? Okay. So for that, we need to define what is the similarity between two vectors. All right. once we can define the similarity between two vectors, we can use that measure to measure the similarity between two employees or between two objects. All right. So similarity is nothing but a numerical measure of how alike two data objects are. Similarity value is high when the two objects are similar, and it is low when they are not similar. Typically, what we do is we perform this similarity calculation in such a way that the result of similarity is always in the interval of 0 to 1. 1 means we are talking of two objects that are 100% identical. And 0 means we are talking of two objects that are 100% different from each other. And every other pair of objects will lie somewhere in between. All right. So that is what we do. And of course, if you reverse the measure of similarity and you do it, you want to calculate dissimilarity, then you can say, all right, if dissimilarity is high, that means two objects are very different. And if the dissimilarity is small, that means two objects are very similar. Okay. Of course, one can say 1 upon similarity should give me dissimilarity. But the reason we don't want to do that, because similarity has a value of 0 also. All right. So when similarity values are very small, dissimilarity will go towards infinity. All right. So typically, what we do is we use the term proximity that refers to similarity or dissimilarity. Depending on the context, you can figure out whether somebody is talking of similarity or somebody is talking of dissimilarity. All right. How do we measure them? So similarity or dissimilarity has to take into account what is the nature of the underlying attributes. So if the attributes are nominal, then if both the nominal values are same, then the similarity is 1. If the nominal values are different, then the value is 0, and so on. Okay, so that shows you how these are done. This is pretty obvious thing. So let's move on to the next one. In order to measure dissimilarity, people generally use the idea of Euclidean distance. Because if you're talking of two vectors, each vector representing an object with certain properties. All right. So if there are 5 properties, let us say, then we are talking of 5-dimensional vectors. That means we are talking of a 5-dimensional space. And what we can do is we can measure the distance between these two vectors in the 5-dimensional space, because each vector is going to be a point in the corresponding space. So the two vectors are nothing but points in that 5-dimensional space. And what we can do is we can measure how far apart those 2 points are. If they are far apart, that means two vectors are quite different. If they are very close to each other, that means two vectors are pretty similar. So typically Euclidean distance is used, and the formula for Euclidean distance is shown here, which is very similar to the distance that you have used in 2 or 3 dimensions. All right, it's the same formula. You basically extend it to the number of dimensions that you have. So take the difference along each axis or along each axis, take the absolute value, square it up, add up all those square distances, take the square root, and that becomes your Euclidean distance. All right. And again, typically before you start measuring the Euclidean distance, you will be doing normalization so that no particular attribute is going to dominate the result. All right. The Euclidean distance, you can say, is a special case of a very generalized distance measure, which is known as Minkowski matrix or Minkowski distance. So the formula for Minkowski distance is shown here. And you can see that wherever I had 2 earlier, to the power 2, I have to the power r. And wherever I had square root of 2, I have 1 upon r. All right. So basically 2 is replaced by r. So if r is 2, the Minkowski distance becomes Euclidean distance. The other 2 values of r are shown on the next slide. If r is equal to 1, then the Minkowski distance is known as the city block distance or Manhattan distance or L1 norm. So basically, in this case, all you are doing is you're looking at what is the difference along each axis, take the absolute value of distance and add them up, and that becomes your city block distance. R equal to 2 is the Euclidean, and R equal to infinity is known as the chessboard distance or L infinity norm. And R equal to 1 is known as the L1 norm. All right. Now, if you think about this, you will see that if I want to plot a contour of points in 2 dimensions from origin that are at a unit distance using Euclidean as a metric, obviously I will get a circle. All right, because every point on the circle is at a unit distance from the origin if the circle radius is 1. All right, and the center of the circle is origin. But if you want to plot the contours for r equal to 1 or r equal to infinity, you will get different shapes or different contours. All right. So I will leave that for you to investigate. And we will stop here. I think we have gone a little slow today, but that's okay. We will stop here. All right. And we'll continue our